Now we end the topic on complex numbers with by presenting you how complex logarithms and general power of a of complex numbers are evaluated. Okay, so we will find that the complex logarithm is more complicated than the real logarithm. Okay, which is really hard to comprehend in terms of its geometric interpretation. That is why we have struggled on understanding this complex logarithm for a long time. Okay, but we will be able to establish methods so that we can evaluate complex logarithms. Okay, and basically, we have already performed um, an example that would actually be a very good basis on how we can proceed, okay, with complex logarithms. Okay, I would like you to review example 7, letter C, under section 1.3 of our lesson. Okay. So that demonstrates, okay, the method that we have used here. Okay. So that is the part where we will have to take the logarithm of one side. Okay. Um in order for us to evaluate the or in order for us to solve this Z, okay, is basically one way, okay, to understand the whole process of evaluating complex logarithm. I'm not saying that that is similar, but this is a very good starting point. Okay, so going back, um, if we have, if you, what we want to do here is to evaluate the natural logarithm of z. Okay, which again, we should say that we should have known from the start that z is a complex number equal to x plus iy. Okay, so if we actually let the number or let the solution for ln of z to be equal to w, okay, then by taking the by using inverse functions, okay, basically exponential functions and logarithms are inverse functions of each other. Okay, um, then we can say that e raised to w equals z. Okay, now note that z is 0 because the exponential cannot be 0. Okay? Now, if we set now your w as a complex number, expecting that the answer to this problem is a complex number, okay? And then placing or writing your z, okay? Writing your z, the given number in exponential form, okay? We will have the following. So we will have e raised to u plus iv, okay? This is your e raised to w. Okay, and now this is your z. Again, e raised to w is equal to z. Okay, and then from there, again we say that e raised to u plus iv, okay, is actually equal to e raised to u times e raised to iv. And when this is equal to r e raised to j theta, or r equals I theta, okay, whether it's I theta or j theta, that works in the same way. Okay, and that is interpreted in the same way. Okay, I'm just using I here because I'm referencing the book. Okay, but in other places, in other courses, you might be using j. Okay, so remember that. Okay. Um. So from here, okay, from this statement, okay, we can establish that e raised to u equals r. And again, we know r because z is given. If z is given, we know r. Okay. And so we can solve for u. Okay? We can solve for u here. In the same manner, e raised to iv equals e raised to I theta. Okay? And therefore, that should mean that v equals theta. Okay? So, that now solves for v. Again, we're trying to solve for w here, which is equal to u plus iv. So, you're determining u and iv. Okay? So from this statement, we can determine u as the natural logarithm of r, which is a real number. Again, r is a real number because that's the magnitude of your given complex number. Okay, so this would be a real number, and therefore u is also the real number. Okay, but what complicates the natural logarithm is the fact that your v, your v here, is actually equal to the argument of your complex, your given complex number. And again, okay, if we are using the argument from the exponential form of your complex number, that means that this is not the only value that is available for us. That is that establishes the location of your point in the partition plane. Okay, so we'll talk about that later. Okay, so now the natural logarithm now of z. Okay, we established now the natural logarithm of z as this one, formula 1. Okay, as the natural logarithm of r plus I theta. Okay, where r is of course greater than 0. Okay, positive. Okay, and you'd be assured that that is positive because you're talking about magnitude. That r is computed from the square root of x squared plus y squared, which is always positive. Okay. And theta there is the argument of z, which is what I have been establishing here. Okay. So again, we will have no problems, or we will have no qualms with whatever uh, the value of the logarithm of r is. Okay, we're okay with that. Okay. What concerns us is this theta. Okay. Again, as I have discussed in the previous sections before. Okay, in the previous section before, in particular, in 1.3. Okay. Um, if we will have the argument of a number, okay, or of a complex number, say, to be used, okay, remember that this is not just a single value that defines the argument, say, and that locates the point on a complex plane. Okay, there are infinitely many um, values for this argument of say. Okay, so um, what we will do is this. What we can say is this. The solution for the problem of finding the natural logarithm of a complex number results to infinitely many solutions. There are infinitely many solutions for this problem. Okay. That starts from the fact that the the imaginary part of your answer is based on the argument of your given complex number. Okay. But we can express that, again, we can express that answer, okay, adding multiples of 2 pi. Okay, since we have already known that the argument is periodic with the periodicity of 2 pi. Okay, we can add multiples of 2 pi to this argument. Okay, so that we can come up with all, or we can write all of those infinitely many solutions. Okay, but we have to establish some boundaries here. Okay, number 1, if we're talking about the notation ln of r or ln of z, we're asking for basically we're asking for the infinitely many solutions. Okay, but if in particular, and it would cause if it would cause confusion, okay, um, we will use the notation ln, or the natural logarithm of z, with L here being an uppercase L, okay, to mean that we are looking for the principal value, or principal value of the natural logarithm of z, which has infinitely many solutions. Okay. Um, Although I would not really fault you if you would be confused with both of these with both of these notations. Okay. So in fact, if in your quiz it asks the problem asks for the principal value, and then you have written ln of z equals something, and then you actually gave the principal value here, I'm okay with that. Ang ibig sabihin, yung notation na 'to is not really critical to me whether it refers to the principal value or um, to the general solution or the infinitely many solution. Okay? It doesn't it won't be really a technical matter to me. Okay? As long as walang confusion sa kanilang dalawa. Okay. If there is if there would if it is if it would rise, if confusion would rise, if by uh, for example, you are arguing that the natural logarithm of z, okay, would be say you would be using in your argument both the infinitely many solutions, okay, and the principal value. Okay, when you're trying to explain something and then you would be using both in your explanation, it would be helpful for you to differentiate the two using this notation. Pero kung nagso-solve lang naman kayo and in the final answer, you have written ln of z, this notation, pero ang nilagay nyo dito is principal value. Okay? As long as the question asks for the principal value, okay, I'm okay with that. Kumbaga, hindi nyo naman kailangan gawing technical na hindi ko maimamali na na sulat nyo, tapos principal value niligay nyo, principal value din naman hinihingi. So, that's okay. Okay. Ang sinasabi ko lang is that kung sa explanation nyo, kung nag-explain kayo, for example, and that there is a confusion between this notation and this notation, then kailangan nyo siyang i-separate. Okay, kailangan nyo establish yung infinitely many solutions and yung principal value. Okay? Also, in problems involving logarithms, in general, ang hahanapin natin lagi is yung infinitely many solutions. Unless stated otherwise by the question. Kung sinasabi ng question na hahanapin nyo lang is yung principal value. Okay, and then give the principal value only. Okay, solve for the principal value only. But if nothing is stated, it by default it means infinitely many solutions. Okay, so here's the relationship between or here's how we determine the principal value. Okay, so we will use the principal argument or the principal value of the argument. As sinasabi ko ito kanina, the principal value of the argument, okay, is that value between negative pi, the smallest angle, okay, that is possible for your, or the smallest angle that is possible for your number. Okay, so that should fall between negative pi and positive pi. Okay, so ayun. And then for you to be able to come up, okay, for you to be able to come up with the infinitely many solutions, okay, you start with the principal value and then you add a multiple of 2 pi for to that. Okay, so basically, what is this form is suggesting is that the infinitely many solution can be written for the complex logarithm is, or can be written as ln of r, okay, plus theta being the principal argument. Okay, theta here is considered to be the principal argument, okay, for your z, plus or minus 2 pi n, okay, times I. Okay, take note, I is on the outside because you have to add this angle to another angle. Okay, and then you would have your n equal 0, 1, 2, and so on. Okay, so that's how you would be able to write. Okay, or that's how we interpret the solutions for your for the natural logarithm of a complex number. Okay, I remember just lang dito that theta here refers to the principal argument of the complex number, of the given complex number. And again, the principal value of that argument falls between or should fall between negative pi to positive pi, the principal range or the fundamental range. Okay? So now, one of the interesting things about the complex logarithm is that even though the thing looks complicated, um, some of the properties that apply to logarithms on real numbers also apply to logarithms of complex number. Okay. Take a look, for example, at this property. Okay. One of the properties that logarithms on the real number domain has is that if you have something like e raised to ln of x, okay, this should be equal to x. Okay. Where x here is a real number. Okay. Now we shall see that this also applies to complex logarithms. Okay. Now let's start with having your ln of z, or the natural logarithm of z, which is equal to the natural logarithm of r plus I theta. Okay. This is what we established in Formula 1. Okay. You may look up there and see that this is your Formula 1. Okay. Now what we will do is we will take the exponential of both sides. So we will have the exponential of the natural logarithm of z. Okay. Of z. Okay. Which is equal to the exponential of the natural logarithm of r plus I theta. Again, take note that the exponential function exp of x is equal to e raised to x. Okay? So, for example, this expression means e raised to ln of z. Okay? I'll revert back to the original to this more familiar form later on. It's just that I have just first written this in this form so that the expression looks more compact, right? So now remember that the exponential and the natural logarithm are inverse functions of each other. Okay. So if you apply the exponential on the logarithm, it cancels the logarithm out, and vice versa. If you apply a logarithm on the exponential, it cancels the exponential. Okay? So something like parang um given that you have theta, okay, and then you obtain the cosine of that theta, okay, and then you obtain the inverse cosine or the arc cosine of that of the cosine of that theta, that should give you back theta. Okay, because arc cosine and cosine are inverse function. Okay, so same thing with this one. Try nyo to, for example, 30 degrees. Okay, try finding what is cosine 30 degrees and then find what is the arc cosine of the cosine of 30 degrees. That should give you 30 degrees. Okay, verify nyo using your calculator. Okay, so same thing with this one. Okay, the exponential function and the logarithm function or logarithmic function are inverse functions, and therefore they cancel each other. Okay, so therefore the exponential of the natural logarithm of z is simply z. Okay, now here um since this is an exponential function, the argument here are exponents. Okay, so therefore you have here um you are adding exponents to a base. Okay, so the base here is e. Okay, and then you're adding the exponents n of r, the natural logarithm of r plus I theta there. Okay, which should give you e raised to ln of r, okay, times e raised to I theta, which again is stems from the property of logarithm of exponentials. Okay, so that should be this one equivalently can be written as e of the natural logarithm of r times e of the natural of I theta. sorry, um, that is basically e uh, raised to I theta. Okay? Now, in the same manner, okay, again, at this factor, okay, shows that you are applying an exponential to a logarithm. So, which means this function should cancel each other out leaving r. Okay? And then, here, you have e here, okay, e raised to I theta, which is your z. And again, from the start, okay, we already said that z here, your given number or your given complex number, okay, should have the exponential form re raised to I theta. Okay? Now that should imply that e raised to the natural logarithm of z is actually equal to z, which establishes this formula. Okay? Now, on the other end, so we were able to establish na nga this property, no? But on the other end, again, we know from real numbers that the logarithm of the exponential, okay, uh, of a real number, okay, is equal to x, okay? So we know this from the realm of real numbers. Now we can establish the same with the exponential of a complex number. But again, this becomes a little too complicated because of the nature of the complex number itself. Okay, which again, if we let z equals x, um, if we let z equals x plus iy, okay, then we can write this as the natural logarithm of e raised to x, okay, times e raised to iy. Okay? Now, again, recall that there is this property of the logarithm that if you're taking the logarithm of the product of two numbers, that is like the logarithm of say um, m times n, okay, that should be equal to the logarithm of m plus the logarithm of n. And although I use the natural logarithms here to establish this, to present this this property of your logarithms, it also applies to any base. Okay, this also applies to any base of your logarithm. Okay, so now we have here the product of two exponentials, uh, which we take the natural logarithm of. So we can use this property to establish that this is equal to the natural logarithm of e raised to x plus the natural logarithm of e raised to iy. Okay? And then, looking at this part, okay, we see that x is a real number. So therefore, this easily applies. Okay, this property easily applies. So therefore, we can easily say that this is x. Okay, because that's x is a real number, and this operation operates on real numbers. So we can just simply use this one. Okay. But in this case, we can also use that one. Okay, use this property. That is, we can say that ln or the natural logarithm of e raised to iy is actually equal to iy. Okay. But then, okay, wait lang. Iy. Okay. But then, remember that this is the argument of your exponential. Okay? And since this argument of your exponential becomes something that is part of a complex number written in written in rectangular form, okay? This would now cause your complex number or your answer here, okay, to become multivalued. Okay? Here, it's okay. Ito kasi sinasabi natin about your exponential being being or having a periodicity, and um, why do we consider them, okay, being multivalued kapag ginawa natin siyang rectangular form. Again, every rectangular, if your complex number is written in rectangular form, it specifies a certain location on the Cartesian plane. It always specifies one unique location on your Cartesian plane. Okay? Um, but in exponential form, okay, a point on the Cartesian plane can be identified by many um, by many exponential complex numbers written in exponential form. This is owing to the fact that your um, argument or your angle is periodic. Okay, so in here, if your number is in the exponential form, okay, it won't matter. It really doesn't matter if whatever angle you have or whatever argument you have for your y. Okay, if you have it as e raised to iy, I times pi over 2, for example, where your y is equal to pi over 2. Um, whether you place pi over 2 there, or what's pi over 2 plus 2 pi, that's 5 pi over 2, or whether you place e raised to I times 5 pi over 2. Okay. Um, this would always point to us to the same point on the Cartesian plane. They would always these numbers would always point to this would always go to the same point on the Cartesian plane. Okay, so that's fine. Okay. However, if we actually take this argument and make it part, okay, make it part of the complex number in rectangular form. Okay, in rectangular form. Um, x plus I times pi over 2 is different from, or specifies a different point from x plus I times 5 pi over 2. Whatever the value of x is. Okay. It would always specify a different point on the Cartesian plane. Okay. Again, in rectangular form, every number there establishes a different point or a unique point on the Cartesian plane. Okay. And since you have written this in rectangular form, okay, these 2 points are now different. These 2 points are the same because they are written in exponential form, and these 2 points are different because they are written in rectangular form. That is why we really, if if we're taking this y, okay, as an argument, okay, for your exponential, for your complex number, okay, and we use it as one of the coordinates, okay, of your number in the Cartesian plane, we really need to consider those different points, the differences in those in the location of those points. That is why we need to specify them. Okay, so in here, okay, the complication here is that we don't have a problem with this part. Okay, so that's simply x, but we have a problem with this part because again, we have here the y, the argument here, which is which when we convert, or which when we use as part of the as a component of rectangular form, or the rectangular form of your complex number, becomes multivalued. Okay, so that is why we have to write this as um, x plus I times y plus 2 pi n. Okay? Where n is plus or minus, let's use plus or minus, where n equals 0, 1, 2, and so on. Okay? Now, we can actually separate y here, okay, by having this written instead that as x plus iy, okay? And then plus or minus 2 um 2 pi 2 pi ni, again for n equals 0, 1, 2, and so on. And so recall that x plus iy is actually the number z. Okay? So this becomes z plus or minus 2 pi ni, again for n equals 0, 1, and 2. And that is where your that is where the natural logarithm of e raised to z is equal to. Okay? So, that is how we establish formula for B. Okay? So, your ln of e raised to z is actually equal to z plus or minus 2 pi and I, where n is equal to 0, 1, 2, and so on. Okay, so that establishes formula for B. Okay? So, that is logarithms. Okay, so let's work on example 10. Okay, so here, what we will try to do in example 10, okay, is to find all the values and then find the principal value. Okay, if you were able to find, or if you were able to establish the all the values or the multi-valued uh, answer for your problem, you can actually obtain the principal value from there by setting n is equal to 0. When n is equal to 0, what usually ends up is the principal value. Okay, and that's in general. Okay, that holds true for most of the cases or most of the problems that we will be able to encounter. Okay, say for example, for letter A, okay, for example 10A, we have to find the natural logarithm of 1. Okay, now what you need to do is to convert 1 to exponential form. Okay, so 1 or 1 plus j0, 1 plus 0i in rectangular form is basically um, r of this, or the magnitude of this is basically 1. Okay, and then its angle, okay, is basically 0. So that's e raised to 0i. Basically because when we say that the number is at 1 plus 0i, okay, it is located here. That is your 1, 0. Okay, that's your 1, 0. So we note that this magnitude, or the length of this radial line that connects the origin and your number, is equal to 1, and the angle that it makes with the positive x-axis is basically 0. So the rectangular form of this one is 1 times e raised to 0i. Okay? So basically, what we're trying to obtain here, okay, is the logarithm of 1, okay, times e raised to 0i. I just have to write it because I would want you to see, or I would want you to see what happens to each part, okay, as we have been able to establish here. Okay. Um, this part kasi, this part actually calls for you to convert the number to polar form, to exponential form, and then simply use the logarithms to establish equivalence. Okay, so that is why we have to convert this first into exponential form, even though that is one in which every part of it is either 1 or 0. Okay, so I still have to write them so that you'll be able to see them. Okay, now from there, you would be able to see that you can write this as the natural logarithm of 1, okay, plus, okay, the natural logarithm of e raised to 0i. Okay, but here, okay, take note, this may be 0, okay, that may be 0. The principal value of that angle might be 0. But remember that 2 pi is also an equivalent angle to this one. Or if you actually write that as e raised to 2 pi I, that should give you the same point. Also, if you actually put it at e raised to 4 pi I, okay, that should also give you the same point. So therefore, this is not just, even though this is 0, even though the principal value of this argument is 0, okay, when it comes down to in writing this in rectangular form, in using this in rectangular form, okay, you would end up with having the multiples of 2 pi as part of your um, solution. Okay? So therefore, we now proceed with having um, here as evaluating the natural logarithm of 1. Okay? Which is basically 0. Okay? We can just simply compute the natural logarithm of 1 here. Because now, since this is r, remember that this is r. Okay? This is r. So we know that this part is really a real number. The difference between this one and this one is that this one is basically a complex number. But when we use this one as an r, okay, or as as an r, okay, we know that r is a real number because it's a magnitude. It defines length. Okay, your length cannot be a complex number. Okay, length is measurable, so therefore it should be there should be a number, a real number that should describe it. Okay, so that's the difference between this one and then this one. Okay, so therefore we evaluate this simply as the natural logarithm of 1 as the real number, and so that is 0. Okay, and then we will have this as um 0i. Okay, but again, given that this argument, okay, this argument is periodic, okay, when it is when it is an exponent of your exponential, okay, that is periodic. So therefore, it should point to the same number. This time, we will write this as a part of your number in rectangular form. So therefore, these are not unique numbers anymore. So that is why we have to um, add, okay, multiples of 2 pi from that principal value, or from that principal argument. Okay, so this becomes 0 plus 2 pi n times I. Okay, or simply writing this one, we will have your ln of 1, okay, as equal to 2 pi n times I, where n, I forgot to write it here. N here is basically 0, plus or minus to. Okay, so basically this becomes plus or minus also. Okay, so this is 0, 1, 2, and so on. So that is the entire solution of your ln of 1. ln of 1. Okay, that is your entire solution of the ln of 1. Okay, just take note that n here is 0, 1, 2, and so on. Now, to find the principal value of this one, we will have to just ignore this part. Or basically, that says that we should just set n to 0. Okay? Because when you set n to 0, 2 pi n becomes 0. So therefore, if we consider finding the principal value, okay, we will write now the natural logarithm of 1, okay, as 2 pi times 0 times I, so that becomes 0. Okay? So, ito yung pinopoint ko kanina. Okay? About the notation of the natural logarithm of the complex number. Okay. If you are just looking for the principal value, okay, it won't matter to me if you have written your final answer as this one or as this one. Okay? Since what is being asked is the principal value. So whether you use this notation or you use this notation, that's fine with me. Okay? That's okay. Okay. But in this case kasi, what you are being asked is to find the multi-valued solution and the principal value. Okay? So for you to be able to differentiate your answers for those two distinct problems, okay, you have to differentiate also the notation. So that is why I use this notation to indicate that this is the multi-valued solution, while I use the notation to indicate, okay, that this is the principal value of the solution. So if there is no ambiguity, it's okay to use this. If it would cause no confusion at all. Okay, but if there is a way, or there is a part of your answer that would cause confusion if you actually use um, a wrong notation, then you should correct it by using the prescribed notation as we have discussed. Okay, that is this one, um, pertains to the multi-valued solution. Okay, and then this one pertains to the principal value of the multi-valued solution. There is a difference between the two. Okay? So I hope this clears things up. Okay. Now, let me try to work on letter B. So in this case, we are to find the natural logarithm of -4. Okay? So this is 10b. Okay, this is 10b. Okay, which is the natural logarithm of -4. And again, we will have to write -4 in terms of a complex exponential. Okay? If you actually locate -4 on the partition plane, you would actually be locating it here. That is at -4, 0. Because -4 as a complex number, okay, as a complex number is um, written as -4 plus 0i. So therefore, you locate it at -4, 0. Okay, which makes it obvious that the magnitude here is 4. Okay, the magnitude is always a positive number because it always specifies a length. Okay, so how long something or how far a point is from the origin. That's a positive number. Okay, that is length, so that should be a positive number. So r here is 4. Okay, and then the angle is goes from here to here. Okay, so that angle is basically pi. So therefore, if you write -4 in terms of exponential or in terms of its exponential form, or which is 4 -4 or -4 plus 0i, in exponential form, it should be written as 4 e raised to pi I. Okay, this is the magnitude, this one, and this is the angle, this one. Okay, so that should mean that you would be looking for the natural logarithm, okay, the natural logarithm of 4 e raised to pi I. Okay, and again, using properties of logarithms, you can simply find this as the natural logarithm of 4, okay, plus the natural logarithm of e raised to pi I. Okay, now, at the start, actually, if you attempt to solve this on a calculator, you would not find any answer. Okay, because the one thing about logarithms is that its argument can never be negative. Okay, its argument can never be negative. Okay, it's basically because it stems from the fact that um when you raise a number, okay, when you raise a number, especially if the number is positive, and the base of the natural logarithm is basically e. Okay, when you raise this to a number, okay, whether that number is negative, say -10, or whether that number is positive, say negative, is e raised to 20, it would always turn out to be a positive number. Okay, so the value of the value of this exponential, okay, would always be positive regardless of um what is the sign of the exponent. Okay, whether the exponent is negative or positive, this would always return a positive answer. So that is why the argument of the logarithm cannot be negative. Remember that this is the answer, this number is the answer to the exponential problem. Okay, when you have, say, for example, e raised to x equals y, okay, um, that means the natural logarithm of y equals x. Okay, y is the answer to the exponential problem. X here is the exponent, and is the answer to the logarithm problem. Okay, so therefore, this number says again, e here, whether you raise e to any number, whether that number is negative or positive, whether that number is fractional, e raised to x cannot be negative. So therefore, y here cannot also be negative. That is why you don't find, or you cannot, the logarithm of a negative number is a complex number or results to a complex number, as we will be seeing here. Okay? So you cannot calculate this on a calculator. It will just return an error. Okay? So there. Now, but here we now find that we need to evaluate the natural logarithm of 4. And we'll leave it at that because we want to make this as accurate as we can. Okay. So, but in this case, in another case, okay, in another term, okay, so we will have here the natural logarithm of e raised to pi, which should give us pi I. Okay. But again, um, this is an argument, okay, that may assume many values, okay, in which if we put it as a component of your number in rectangular form, that should always appear. Okay, so what we will do is, this is the principal angle, okay, and then we will add the multiples of 2 pi from there, okay. So, that is basically this one. 4n equals 0, 1, 2, and so on. Okay, so that would be the natural logarithm of negative 4. Okay. Now what the answer here did was to factor out pi here. So if you actually factor out pi here, that becomes the natural logarithm of 4 plus um, 2n plus 1 um, times pi I, where n equals um, 0, 1, 2, and so on. Okay? And the principal value, so that's the multi-valued answer or solution for the natural logarithm of negative 4. Okay? So we find now the principal value of the natural logarithm of negative 4, which is, we can find that by setting n is equal to 0 here. So we find that the principal value of the natural logarithm of negative 4 is the natural logarithm of 4 plus pi I. Okay, so that is pi I. Okay, so that is simply obtained by setting n equals 0 here. Okay, so that would be the principal value of the natural logarithm of negative 4. Okay, so it's a complex number. As I said, as I stated here, your natural logarithm cannot have a negative number as an argument. Okay, as an argument here. So therefore, if you are evaluating the natural logarithm of a negative number, that should result to a complex solution. So we can see it here. We can clearly see it here. Okay, that this one has no real solutions. Okay. Now, I think I have given you enough demonstrations in order for you to be able to solve letter C and letter D. So here are the answers. You may check your answers against these answers here indicated, just to see that you are working towards the right direction. Okay, so there. Now, as I said before, other properties of the natural logarithm hold that are established using real numbers actually apply to complex numbers as well. Okay, so something like this one and then this one. Okay, actually this is something that I have stated and used in a discussion earlier. Okay, if you can go back there. Okay, I used the equivalent expression of that in real numbers, that is the natural logarithm of m times n, okay, equals a natural logarithm of m plus the natural logarithm of n. And again, as I said, if we have established this using real numbers, turns out that they also hold true for complex numbers. Okay. Now, finally, we now proceed with the very last topic of this section and of this topic also, which is evaluation of general powers, okay, of complex number. When you say general powers, it means that you have a complex number raised to a complex number, okay? So the way to evaluate that is using this formula. But I'll show later, I will show through examples how you can establish this formula. Basically, we'll do it now, okay? So our problem is that we have a complex number C, Z, to be raised to a complex number C, okay? So here, we assume that Z cannot be equal to 0. Okay. So how do we do this? We first try to equate this to W. Okay. So our answer would be in terms of W. Okay. Now, what I would do next is something that is familiar, something that we always do when when we have when we have problems dealing with exponential expressions. Okay, so that is we will have to take the logarithm of both sides. So we will have the natural logarithm. Okay, we have the natural logarithm of um, z raised to c. Take note z and c here are both complex numbers. Okay, and then this is equal to the natural logarithm of w. Okay, now again, my answer or my solution to this problem, this is my problem, and the solution to my problem is in w. So therefore, I would want to solve this for w. Okay? And for me to do that, okay, for me to do that, you can go back to formula 4a, okay, above, okay, which states that which states that e raised to the natural logarithm of z is actually equal to z. Okay? So that is your formula 4a, as I remember. Okay? So for us to be able to get w here, okay, I would use this one. Okay? So since this is this right side is the natural logarithm of w, I could apply exponentials on both sides. Okay? Which is basically this thing. This one is this thing. Okay? So I'll also apply exponential here. Okay? But before that, before I apply the exponential on this side, I would have to rewrite first this. Okay? I would have to rewrite this first as um, c times the natural logarithm of z. Okay, remember that we have again that property of your logarithms. Okay, that is when you have something like um, the natural logarithm of m raised to n, that should be equal to n times the natural logarithm of m. Okay, and that is established again using real numbers, but then again, it is possible to show that this also applies to um, complex numbers, and they also apply to complex numbers. So therefore, I can rewrite this expression in this manner. Okay, and then that's the time I would take the exponential of that expression. Okay, so again, take note that the exponential and the logarithms are inverse functions of each other, and so they cancel each other out. So this becomes w, and then this side can be written as e raised to c times the natural logarithm of z. Okay, and therefore, if you can remember that w holds the solution to my problem, which is z raised to c, and that is equal to this expression, which is e times c, uh, e raised to c times ln of z, as what is pointed out by formula 7. Okay, so there. Now, there are there are two ways of actually working on general powers. Okay, number one is to actually apply this formula. Okay, you need to apply this formula. That's you need to identify what is C, what is Z, and then since there is a problem of finding the ln of Z here, you have to evaluate this as what we have discussed in the previous topic, in just the previous preceding discussion. Okay, and then multiply it to the complex number C, and then apply the exponential there. So you would have this number. Another way is to use this sequence. Okay, so that is you use a variable to hold the answer. Okay, you get the exponential, the logarithms of both sides. You apply exponentials on both sides, okay? But first applying the logarithmic property on the left side, and then you can now solve for your w, or the variable that holds your answer. Okay, so let me demonstrate that sequence, or let me first demonstrate the use of this formula with example 11a. Okay, so this is 11a. Okay, so this is 11a. Now, we are to find the value of I raised to I. Okay, here j is equal to I, and c is also equal to I. Now, first, I would like to I would like to first convert or express z in terms of polar form, because I would have to evaluate the logarithm of this later on. And again, if you want to evaluate the logarithm of a complex number, you need to find the um, you need to find the you need to write the complex number in exponential form. So this is I is e raised to I pi over 2 in exponential form. Okay, so let's let the answer to this as w. Okay, and then let's take the logarithm of this one as the logarithm of um, I raised to I. Okay, I raised to I becomes the logarithm of w. Okay, and then apply natin yung property ng logarithm dito, which makes this I times ln of I, okay, or the natural logarithm of I equals the natural logarithm of w. Then let's take the okay. Let me redo my solution because I felt like I would lead you to a confusion. Okay. So let me redo the solution. Okay. So again, as I stated, there are two approaches to do this problem. Okay. Number one is to apply the formula directly. Okay. And number two is to use this approach, or use these steps. Okay. So let me first apply the formula. Okay. So the formula says that z raised to c, both of which are complex numbers, is equal to e raised to c ln of z. Okay, this is formula number 7. Okay, so here we identify that z, in this case, we identify, let's put out this w first. Okay, we identify that z here is I, and c here is also I. Okay, so therefore, I raised to I, based on this formula, is e raised to I times ln of I. Okay? So that is how you apply the formula. Okay? Now, let us take this problem, this problem down into steps, starting with evaluating what is ln of I. Okay? What is ln of I? Now, again, if we evaluate the natural logarithm of a complex number, we need to find, or we need to have the exponential form of this complex number. Okay, which should be pretty easy to determine, that is e raised to I times pi over 2. Okay, this should have been something that is really familiar to you, because this is something that we have already established in the past lessons. Okay, so that we have here the ln of I, and I here is e raised to I times pi over 2, so that when we evaluate this, okay, we identify that r here is 1, okay, and that theta here, okay, is pi over 2, at least the principal value. Okay, but including the other values, okay, we need to add multiples of 2 pi to the principal angle, or the principal argument. Okay, again, taking note that n here um, is equal to 0, 1, and 2, and so on. Now, you might be asking yourself, why is why is there always why do we have to really write this every time we establish this? I believe so that you have to, because that helps you interpret the problem correctly. Okay, it's not just putting this as a sort of formality, but actually trying to ingrain in your mindset that that is how you interpret and that is how you write your solutions in complete details. Okay, because that reflects how you are that reflects how you are thinking about the problem, your mindset on how to think on solving the problem, and also how to report your solutions. Okay, so I always see to it that every time I establish this, every time I use this part, that I have to write this, because that helps me put the problem in perspective and make me correctly interpret the problem. So that should be your practice as well also. Okay. So again, theta here is pi over 2 based on this one. But again, we need to consider adding multiples of 2 pi here, okay, to consider the multi-valued nature of this argument. Okay. So therefore, ln of I, okay, or ln of Z, basically, recall from the previous section that ln of Z is ln of R, or the natural logarithm of R, plus I times theta. Okay, so therefore, ln of the natural logarithm of I is equal to ln of 1, or the natural logarithm of 1, this is R, okay, plus I times theta, which is, we establish here as pi over 2 plus or minus 2 pi n. Again, for n equals 0, 1, and 2. Okay? Now, we evaluate now the natural logarithm of 1 with 1 as a real number. And so we find that that is 0. Okay, so therefore, we were able to say, or we will be able to say that ln of I, or the natural logarithm of I, is equal to I times pi over 2 plus or minus 2 pi n. Again, for n equals 0, 1, 2, and so on. Okay? Now, the next thing is that here, you can see that you have to multiply ln of I, or the natural logarithm of I, to this number, which is I. Okay? So we evaluate now I times the natural logarithm of I, in which we find that the natural logarithm of I is this. Okay? So we now have here I times I times pi over 2 plus or minus 2 pi n. Okay? With n here equal to this one. Okay? And here, we have to multiply I times I. Okay? So, from there, we see that that is I squared. And I squared is equal to negative 1. So, this becomes negative of a negative pi over 2 plus or minus 2 pi n. For n equals 0, 1, 2, and so on. Which now, um, which now allows us to evaluate now the entire thing. Okay, so that is I raised to I, okay, equals um, e raised to I times the natural logarithm of I, which is this one. Okay, so this is just for a more compact uh, notation, I'll use the functional form of the exponential function, which is exp. So exp of negative of pi over 2, okay, plus or minus 2 pi n, okay, for n equals 0, 1, 2, and so on. Okay? Or we can actually multiply the negative 1 here. We can multiply it around here, so that this becomes, or I raised to I becomes e raised to negative pi over 2. Okay. Now, if you multiply negative here, the positive uh, things here becomes minus, and the negative numbers here becomes a plus. So therefore, this becomes minus plus if you multiply the negative 1 from here to here. Okay? So that this sign becomes inverted. It becomes minus and plus. Okay? So this is minus and plus 2 pi n. Okay? Again, n here is from 0, 1, 2, and so on. And as you can see, I am writing it as often as possible. Okay, I am writing this value of n as often as possible in order for me to really say that um, I really do understand what is the implication of having your number being multi-valued. Okay, so there. So now this is to what value your I raised to I evaluates to. And here's the interesting about this one. The principal value of I raised to I, okay, is found, when um, we set n equal to 0. Okay, when we set n equal to 0, okay, this expression becomes, okay, so the principal value of I raised to I, okay, is um, e, okay, raised to negative pi over 2. Okay, and again, if n is 0, this term becomes 0. So therefore, what is left is this negative pi over 2, which is a real number. Take note that your problem involves raising a complex number by a complex number. And it turns out that one of your answers is actually a real number. Okay, so that is something that is interesting on this part. Okay, so kagaya nung kanina, meron akong problem that seems very simple and involves only real numbers. Okay, but then it turns out that that problem doesn't have a real solution, not a single one. Okay, here you have a problem of raising a complex number by a complex number, and it turns out that one of the answers is a real number. Okay, so these are some of the wonders of your number system. Okay, so there. Now I would really hope that you would be able to work on letter B. Okay, and by the way, I just have used the formula here. No, I used this one. Okay, I can actually not rely on formula and say that I can solve this by um, having I raised to I equal W was with what I did here. Okay, I would just follow what I did here. Okay, so I raised to I equals W. Okay, you apply logarithms on both sides. So if you apply logarithms on both sides, you would have the natural logarithm of I raised to I equals the natural logarithm of W. Apply the property of logarithm here. Okay, so that becomes I times the natural logarithm of I equals the natural logarithm of W. And then solve this one. Okay, previously we have found that the solution for that one is basically um, that is pi over 2. Okay, plus or minus um, oh sorry, the solution there is so this I is this I, and then the solution here is I, okay, times pi over 2 plus or minus 2 pi n, okay, which is equal to the natural logarithm of W. Remember that W holds our solution. So I need to solve this for W. Okay. So your n here is equal to 0, 1, 2, and so on. Okay. Now, first, let's evaluate this part. Okay, so we evaluate this part by multiplying I here. So that becomes I squared. And so that becomes -1. So this is negative of pi over 2 plus or minus 2 pi n, okay, which is equal to the natural logarithm of w. And then that's the time that we need to solve for w. Okay, so that's the time we apply exponentials on both sides. Okay, so we apply exponential here, and then apply exponential here. Okay, again, exponential function and logarithmic functions are inverse functions of which. So if you apply them both to the same number, they actually cancel each other out, and that becomes w. And here, your answer is e raised to negative pi over 2, okay, plus or minus 2 pi n, okay, where your n is 0, 1, and 2, and so on, okay. So we were able to get the same, I forgot the parenthesis here, but we were able to get the same answer as this one, okay. I oversee, akala ko kasi may I pa to, no? So, ibig sabihin pala, lahat pala ng solution nyo ay real numbers. Whether is the principal value or the rest of the solutions, all of them are real numbers. Okay? So, ayun. I said kasi na isa lang yung real number solution niya, but it turns out, akala ko kasi may I ito. So, wala pala siyang I. So, therefore, this is, all of the solutions are real numbers. Okay? So, there. So, this approach uses the formula. Okay? And this approach uses the manner by which I derive the formula. Okay? So, I hope you can choose which approach would be much easier for you to follow. Okay, and I hope that you work on that approach. Okay, and you practice that approach using this problem. Here's the answer. I would like you to find this. I would like you to practice finding this answer or this answer. Okay, using the approach that you have used, whether you use the formula itself or you use this more freestyle approach, which really relies on your knowledge of logarithms. Okay, so I hope that you have that you find time on working this example 11b. Okay, now now that ends up our topic, our discussion on section 1.5, and that also ends up our discussion on complex numbers. Okay, so I hope you were able to establish a certain knowledge on complex numbers, which will be very useful later on, not just here in our own in our course, but also in future courses that deals with topics that rely on complex numbers as a prerequisite. Okay, so there.